So it's our great pleasure to have Gerhard Weikum here with us. Gerhard from the Max Planck Institute in Germany, in Saarbrücken. Gerhard is a big mover and shaker in the database community and beyond. I'm not even going to start telling you everything that he did. My understanding of the German university system is that when you're a professor, you have this little kingdom, and so you're sort of a king in the university. But then there is one step beyond. That's the Max Planck Institute. So if you are a king at the university, I have no idea what you are in the Max Planck Institute. But anyway.
Thank you, Alon, for the introduction. Thank you for your interest in this talk. Now let me elaborate on Alon's introduction. So there is a comparison, what's heaven on earth, and the answer is it's being a professor in Germany. But then there's the downside, what's hell on earth, it's having colleagues in your department or institute. Don't take this seriously. So this is about peer-to-peer web search, an ongoing project that we're working on called Minerva. It's work with a whole bunch of students and also some Mediterranean collaborators. So that's the fun part of being involved in European Union projects. You have these project meetings in interesting locations like Greece or Rome, for example. So peer-to-peer is this charming paradigm that promises to be ultra-scalable and self-organizing. It comes in different flavors. It has applications. Some of them are more toy applications, but others are commercially successful, like file sharing or IP telephony. And so the question that drove us was, is there any application that's useful and legal at the same time? And actually, because I'm in academia, the more important thing for us was also, is there something that is scientifically challenging, as opposed to just doing engineering for in order to become a millionaire or billionaire. So, and I believe that peer-to-peer web search could be such an application. And this is why we're working on this with the Minerva project, and we have a little prototype system running. So the vision that drives us is that each and every, say, power user, like a graduate student or a scholar or a journalist, a market analyst, they could have a power search engine that just runs on their own computer, PC at home, in the office, or your notebook, or at some point your PDA. And that's good enough to have a little corpus locally available, say a few billion pages. And that's probably enough in order to cover most of your information demands. So that could be compiled by using technology like focus crawling, using classification, and so on. And then most of your queries would be answered by your own personalized power search engine, most of the time. But occasionally, the 10 million pages that you have is not good enough, or you're missing some fresh result, and then you should talk to other search engines. And this is why peer-to-peer search is actually a network of search engines, millions of them in the ideal case. So this is the vision. Why is it interesting to work on this? Well, it's not an end by itself, but it's a test ground for more foundational work on scalable and self-organizing data structures and algorithms. You see a few examples. But I do believe it has a potential to boost also search result quality. And there's 3 arguments along this route. One is that the load per computer in this envisioned system is much lower than the load per computer in a big centralized server farm like you guys have here. So that allows us to run much more powerful, fancier techniques, mathematically more advanced techniques that are computationally more expensive. Or, for example, run deep natural language parsing over text pages and represent the text in a much richer way. You wouldn't want to do this with billions of web pages on your big server farm, but with publications in this network, scholarly network, for example, you might want to invest these resources. Number 2 is leveraging user input and community input. That could be explicit assessment, feedback, or implicit behavior given in the form of query logs, click streams, and so on. And this can be done at the individual level or at the community level, and then we're talking about the popular term wisdom of crowds. Now this can be done with a centralized search engine too, and probably it's being done. But that some people in the world are scared by this thought, and might have privacy concerns. And so in some sense, the peer-to-peer paradigm is a natural habitat for doing these things. Because at least in theory, users can directly control the extent to which this information is monitored, to which extent it's shared, to which extent it needs to be anonymized, and they can revoke whatever they allowed the system to do. As I said, in principle, whether mass users are able to handle this is a different story. And number 3 is, if your local search engine is not smart enough or doesn't have enough data, you can collaborate with other peers, so you forward your query, your information demand to other peers that help you along these lines. Now, each of these entails lots of research issues. This is a long-term vision, so I'm not saying that we have this running in a convincing manner within a year or two. There's some sociological and political dimensions. As I said, in my idealistic view of the world, I think the world would be better off with lots of different search engines, smaller or medium-scale search engines, maybe in addition to some big ones that satisfy most of the mass user demands. But oligopolistic situations are not considered healthy in the view of some European minds. So at this point, you should stop me actually and say, well, this is interesting, but has nothing to do with reality. So is this a solution that solves some non-existing problems? And indeed, I don't see a killer app with rich business value here, but I think it's nevertheless an interesting research direction. One thing is the technology may be interesting in other settings, like if we have algorithms of the kind that I talked about, they might be applicable to server farms as well, maybe in some different flavor. And then there are some intriguing applications that may not have business values, but I think they have society value. And here are 2 of them. So one is a scholarly search engine. Now, Google Scholar does a great job on bibliographic data, but it doesn't address the content of the publications. And then actually, we would like to go one step further and represent the content not just in text keyword form, but in more explicit knowledge form, extract entities, relations, and so on, make this searchable in a richer manner. This is one direction, and XML could be a syntactic format for this, but there might be other approaches too. And you need then information retrieval on that richer knowledge representation. Here's just an example query which should tell you this is not the kind of query that google.com would expect to see. The other application here would be web archiving. So I'm not up to date on the numbers that of the page versions that the Internet Archive has. That's a laudable effort to archive the history of the web. But I'm afraid it can't just keep up with the high pace that the web is evolving at. And on the other hand, the history of the web, all the versions that pages go through, is very interesting. It reflects the born digital content of the internet. It reflects culture and subculture and near-term history. So sociologists, politologists, historians are all interested in these kinds of things. Even people like lawyers in intellectual property rights are interested in this. Like patent offices are highly interested in the history of when things were published on the web, in which versions, and so on. So, of course, we would not just want to archive, we would want to provide also richer querying and data mining capabilities covering the time aspects of this. And here are again 2 possible examples of where this might lead to. Now, this talk is not about any of these. We're working on this, but these would be different talks. So if you're interested, talk to me offline. Okay. So this talk is about the peer-to-peer aspects. And one of the main aspects here is the query routing issue. So when I have a query and my power search engine is not good enough to answer it, to which other peers should I forward it? And this is the first part of the talk. Then link analysis, PageRank-style link analysis makes sense in this setting too. But then it incurs extra complexities. So that's part 2. And if time permits, I can talk about some ongoing work that we've been doing on personalization and community-aware ranking. That's not really specific to peer-to-peer, but it fits very naturally into this setting.
By the way, if you have questions, interrupt me anytime. So the computational model that we pursue is like this. Peers are connected by some overlay network. It might be a distributed hash table like court or pastry, but it could be other topologies as well. And in addition, we can talk directly to peers if we know their IP address. Each peer has a local search engine, so it comes complete with a crawler, maybe a focus crawler, indexer, query processor, and so on. The peers are autonomous. This is a point I would like to emphasize, at least in this vision where every professor, every graduate student in the world would have a power search engine. They want to compile their own content. Maybe they produce a lot of content too. So we don't have control over how the content is distributed. We just assume the peers have whatever they have. That entails that the peers might overlap in their content. And to some extent, this is not bad. Some redundancy might actually help. Queries are executed locally first, and then we route them, if necessary, to a carefully selected set of other peers. We're thinking of routing it to maybe 5 or 10 peers, not 1,000 or 10,000, no massive flooding of messages here. So we want to be cost beneficial. And finally, to achieve this routing, we assume that peers post summary information about their content and maybe also quality of service properties that they can offer to the entire network. And this is posted conceptually to a network-wide directory, but that network-wide directory can itself be implemented by a distributed hash table, for example. So it's perfectly decentralized, scalable, failure resilient, and so on. An important point to make here is that this is different from just using the complete text index that a full-fledged centralized search engine would have and making it distributed. The granularity here is coarser than you would have in the actual index. In the actual index, you index documents or pages, web pages. Here we index peers. So that's several orders of magnitude less. The actual page or text indexes would sit on the individual peers. So that's important for scalability. This is the illustration of this with our concrete system, Minerva. So we have the peers connected. They have their local indexes, contents and indexes. They post information. Now here it's organized in terms of searchable features or terms in IR terminology, keywords in typical web search jargon. So for one term, we have a list of peers that have information, good pages that contain these terms. And this is not just the peer list, but every entry comes with some quality measures, statistical measures that tell you how strong is that peer about this term, how good is it, the content that it can offer for this search term. And that's distributed using the hash table, right? Distributed hash table. We can post information about bookmarks. So every peer or the peers that want to post some subset of their bookmarks or social tags, whatever they have to offer, can be posted the same way. So here in one of these directory peers, which it's just a role. All the peers serve also as directory peers. So here for URL-Z, we know which peers have that URL as a bookmark. And then when a query comes and it's issued here, executed locally first, and then we need to solve that query routing problem. So that should aim at optimizing some benefit-cost ratio measure, taking into consideration peer content quality, content overlap, freshness, authority, and so on. And I will give one specific approach for dealing with this. The issue is much broader. I cannot cover all this, and I don't have a good answer for this all-comprehensive issue anyway. So it turns out this is a decision we make at query runtime. When we see the query, and after having it executed locally, we think about which other 5 peers we want to involve in that query execution. So it's already part of the user-perceived response time. And that puts stress on this, what we can do at this point. So another approach would be to pre-compute frequently made good decisions. So when we realize, so most of the time, it makes sense to send this query to the following 5 peers. So if we can come up with some pre-computation of that kind, we can rewire the network or wire an additional overlay network. That is sometimes called semantic overlay network or maybe social overlay network. And it would just make the best peers that help me typically in my queries my neighbors. So then the query runtime decision is sped up a lot because I only need to talk to like a handful of neighbors. Okay, so now the principle for making these routing decisions is we should be driven by a benefit model and by a cost model. The cost model is pretty standard. It's not trivial, it's not solved, but we can build on like 30 years of research in distributed performance modeling and so on. So there's nothing new here. So I will focus on the benefit part. So benefit of a peer PI for a given query should be the quality of that peer or the peer's results for the given query. And we can decompose this into two parts. One would be, so how good is that peer's data content? I call this XI for index I with regard to the query queue. And how good is that peer with regard to the query originator's overall interest profile? So as measured, for example, by the originator's own content called X0 here. But it could also be measured in terms of the query log of that guy. So if I have a query log is nothing else than a local corpus. You can build statistics over that, similar to the kind of statistics you build over an actual text document corpus. And there's there's two possible routes here. For the query part, we use probabilistic IR models. There's old work in distributed IR before the days of peer-to-peer, so-called Cori model, which builds on probabilistic IR. Maybe you heard about, or some of you should know about the Okapi BM25 scoring model. This is one particular instantiation of these kinds of models. So that's pretty standard. Given a query and given a corpus, or here the entire corpus of the peer serves as a document, we compute some goodness score. And that's typically pre-computed per term, and then when the query has multiple terms, we aggregate over the goodness scores of these per term scores. For the part where we compare entire peers, like how good is this peer with respect to my peer's interest profile, statistical language models make a lot of sense. In fact, I think we could argue this is a marriage made in heaven, because statistical language models is like the most principled approach in IR these days, or widely viewed this way, but it suffers from some problems, like often you need to build these over very sparse spaces, so parameter smoothing becomes a big issue. Now here we don't do it on a per document or per query basis, but per peer content basis. So that's a much richer corpus, so it comes with its own background model already, so parameter smoothing should be much less critical here. And it leads to measures like this here. This is one particular instantiation of one kind of statistical language model that leads to the notion of relative entropy or Kullback-Leibler divergence, measuring the similarity of two peers' data contents. So if I'm a sports peer, the other sports peers with lots of good sports pages should become similar to me and should score high with regard to this metric. So I already mentioned, so all that is also the KL part is pre-computed per term, and then as I know the query, or well, for the KL part, because I'm comparing entire corpora, I actually don't depend on the query, but for the other part, I aggregate over the terms in the query at runtime. Now there's one caveat which I want to address. So far I don't elaborate on this because it's pretty much standard IR, state-of-the-art standard IR, applied to the peer-to-peer setting, and maybe some adjustments, but they are not very earth-shattering here. Now, the peer-to-peer similarity, both the query part and the peer corpus part, kind of overfits to content quality. So if I'm a sports peer and I have great web pages, I just talked to Alon about the soccer championship. I have great web pages about the soccer championship, and now, but I want to find something else. I want to find some additional comments or analysis of the matches and so on. So, and maybe my query gets routed to Alain's peer, because he also has a lot of good information about the soccer championship, but what if he has exactly the same pages, because he did the same kinds of focus crawls over the same kinds of parts of the web. So that's redundant. I get great results, but I had them already. The whole point of my local search engine, of that peer-to-peer system, is that I benefit from my local resources. So what I want is, I want not just good results, I want good additional results, new results that I didn't know before. So we need to consider the overlap of the contents of these peers. So this is work we did like in the last 1 or 2 years. Adding some overlap awareness. So we need to estimate the overlap between two corpora, essentially, between two sets of units, web pages in this case here. And we employ a technique that has been pioneered by Andre Broder under the name Minwise independent permutations. That's an efficient synopsis for estimating overlaps between large sets. He actually invented it in a different context, namely for finding near duplicates of web pages, and applied it to like shingles, engrams, if you wish, taken from the content of web pages. And I have a slide explaining this on the one slide later. Just assume now we have this. So we have some way of estimating the overlap between two peers, and we can pre-compute this because this is not query dependent, and we post it also to the directory. Can be posted on a per peer basis or on a per peer and term basis. So for each term, which documents does that peer have? So that's a set, and conceptually that set is posted to the directory, but in the implementation we post this MIPS structure, which is a compact vector. So think of 100 integers, no bigger than this. And then at runtime, we can actually consider the quality of a peer and the overlap with regard to the query originator. So overlap PJ P0 means, so when I ask Alain to help me with my query, does he give me new results or does he give me the same good results that I already had? And as always, so there's no miracle here. So combining these different things typically leads to linear combinations as one approach, right? And with parameter tuning, but we can use feedback and regression and whatever else in order to tune the parameters. So that part so far takes into account the overlap between some candidate target peer, PJ, and myself. But if I ask multiple peers, not just Alain, but maybe Yossi, whom I see here in the first row, so then I want to consider also the mutual overlap between these multiple target peers. So I want an incremental notion of novelty, and that's defined here and can be derived from these pre-computed overlap measures. And then actually I proceed at query planning time in some incremental greedy manner and pick peers for query execution in order of integrated quality novelty, this measure that's defined above. So here's one slide on Minwise independent permutations, which I really think is a cool technique by Andre. So we're given a set of IDs, say URLs, and we want to represent them in a compact manner. Now, conceptually, we compute a set of random permutations of this set of IDs, or a list of IDs, view it as a list. And for each permutation, we remember the minimum. This is where the name comes from. Now, the implementation just uses the hash functions from some family, and instead of remembering the first in the permutation, first element in the permutation, we can equivalently remember the minimum hash value. This is what we do. This is the representation then of this set, and it can be a huge set. And we can do this with all kinds of sets, in particular with different peers. And now we can compare this MIPS representation, this MIPS synopsis of one peer against that of another peer. And the number of identical elements compared to the entire length of this vector gives us an unbiased estimator of overlap. So you can also think of this as some sampling procedure over the space of pairs taken from the two sets. So that's a very efficient technique, and we work with like 128 integer vectors, something, or 256, no bigger than this. So here's some experimental results. So we work with, well, you guys would say toy corpora, but we work with what's available. So that would be a request of mine. If you guys want to help academic research make resources available, well, corpora is not the real bottleneck. Queries, query logs, clickstreams is a bottleneck. So the academic research community would certainly appreciate if Google could make something along these lines available. So here we work with the data from track benchmarks, old crawls of the .gov domain, and also using their queries because it comes with relevance assessments from the track benchmarks. So we compare here two techniques. The Cori baseline is like the best, some of the best known techniques for quality-only query routing. And this is the green curve, and the blue curve is our technique, which adds overlap awareness. On the horizontal axis, you see the number of peers that we send the query to. So that's dealt with as a parameter here. And on the vertical axis, you see the quality measure, or success measure, the relative recall, which is the recall relative to a centralized search engine. So in a search engine, what are the results, best results for the query, and how many of these do we get in the peer-to-peer setting as we ask more peers? And the data is distributed across peers in some random manner, but with a bias so that we construct specific overlaps where we can vary the parameters of the overlap in a systematic manner. And you see that, for example, Cori with 5 peers gets like 30% relative recall. We get 55. And if we give ourselves a target, like we want to achieve, let's say, 80% of the recall that a centralized setting would give us, then we could do this with, say, 7 or 8 peers. And you see that Cori needs almost 20 peers, or 20 or even more peers. So I'm going to skip this one here. So this overlap awareness is an example of distributed statistics management. This is the actual overriding theme here. I think really peer-to-peer web search is about distributed statistics. If you understand this, you are pretty close to understanding peer-to-peer web search. So here's another example. This is estimating a measure called global document frequency. How many documents overall does the network have with a certain term? So we're interested in this for each and every term. And we're interested in this for 2 reasons. One is for something which we've coined discriminative posting, was explained in more detail on the slide that I skipped. So sometimes it's better for a peer not to post summaries on each and every term, but if I'm a sports term, I have a lot to say about soccer, matches, penalty, goal, whatever terms of this kind, and I have little to say about technical terms like, I don't know, LSI, SVD, or whatever, or spectral analysis. So that is used rarely in soccer. So I would want to post only when I think my local document frequency is high compared to the global document frequency. So I need to have an estimate for global document frequency in order to do this. But if I have that estimate, I can do it, and that saves a lot of network bandwidth and makes the direct network directory slimmer and simplifies the query routing decisions. Another reason for being interested in GDF is result merging. When I get back results from 5 different remote peers, they come in an unnormalized manner. So they come with scores, but they are computed based on local statistics and maybe even very different local models. So the best way, the most principled way of merging them in an intelligent manner is to recompute their scores, but then I need global statistics. I need global document frequency for that. So that's used, GDF is used in TF-IDF, but also in probabilistic IR, and it's everywhere. You need it for everything. So that would be an interesting topic, but maybe not too hard if the peers had the world nicely partitioned among themselves. So no overlap between peers in terms of their content, but this is what our scenario is about, right? We emphasized autonomy of peers. This is why we're saying we're a peer-to-peer system. Otherwise, we are a top-down, pre-planned centrally administered distributed system. This is not what I understand by peer-to-peer. So overlap is part of the game, and turns out we have a very elegant solution, which is very simple because we need two ingredients for this. The ingredients are not so simple, but they are not ours, and we just put them together and count 1 and 1 is 2, and it works very elegantly. So there's nothing deep here, but it's very elegant and extremely useful. So one of the ingredients is hash sketches, and Yossi has worked on that too, but then we refer to some older paper. And the other ingredient is distributed hash tables. So let me quickly go over the hash sketches. This is a probabilistic counting scheme, originally invented by Flageolet and Martin. And then forgotten for 10 years, and then Yossi was one of the pioneers who rediscovered it and extended it and came up with new results. And it's a cardinality estimator for the distinct elements in a multiset. So this is exactly what we're talking about because of the overlap situation. The way it works is it hashes, and there's several variations of this. This is one of them, and maybe it's a bit oversimplified also for the ease of understanding. So we hash each multiset element onto a bit vector, and we remember the least significant 1 bit. So this comes in different variants. And then the maximum of these least significant 1 bits is a biased estimator of the cardinality after duplicate elimination. So the bias is, of course, the tricky part, but Flageolet analyzed this. So once we know that bias, we can compensate for this. It has relatively good standard deviation, but for practical purposes, that's not good enough. So it's still can be off quite a bit. So what we do here is some smoothing or statistical averaging. We recompute this multiple times using different hash functions, and then we average. So that works very well and leads to very accurate estimates. So just to give you one intuition about this technique, so after the hash, half of the values is odd and half is even. So the probability of the least significant 1 bit being bit 0 is 1/2. The probability that this least significant 1 bit is bit 1 is 1/4, that it's bit 2 is 1/8, and so on. So if the max of these least significant 1 bits is less than k, this is good. This kind of looks intuitive now. Hopefully, this should indicate that the set is small, right? And actually, it holds in both directions. Otherwise, we cannot use that. So, and here is how we combine it with distributed hash tables. And the observation here is very easy, but elegant, as I think. So distributivity is free. So the union of hash sketches is the hash sketch of a union because of the way they are designed. So, and then we can run global document frequency estimation. I will not go through the text. I will animate it in the following way. So suppose here's one peer, this guy, and all the peers also serve the role of directory peers. So they have data, they are standard peers, but they also help the network with maintaining the directory. And there can be replication for these directory entries anyway. So this guy now has hash sketches for terms ACT and needs to post them to the directory. So they are just sent to where they belong using the distributed hash table. We use chord or pastry, but you can use other techniques. Then this guy happens to be one of the directory peers for this term T. So this is the hash sketch this guy got from this peer. But then the other peers have this term too. They post it too. And then what happens is that a simple bitwise OR computes the right hash sketch because of the distributivity. So then this is the correct hash sketch. Actually, there are multiple hash sketches for the statistical averaging. And this is a fairly accurate estimator. So if any peer wants to know the global document frequency, all you need to do is check out, using the distributed hash table, which is the responsible directory peers, one of those, ask the guy, and the guy can give you the estimate using these hash sketches. And this can be maintained dynamically as data evolves. I'm going to skip this, because this only shows that it's accurate, but this is also in papers. Okay, any questions so far? Okay. So as for the further plan, I will talk about now the link analysis, and I'm in the interest of time, I will skip the third part. I already thought this might be tight here. So, okay. So again, interrupt me anytime if needed. So PageRank, of course, if there's one place in the world where you don't need to explain the PageRank equation, it must be here by definition, right? Any questions on this? Can I take a random exam? Alon, why don't you explain me the role of the dampening factor epsilon? Okay, no, I guess, I mean, we don't get much into technicalities. The key point is that we have this recursive equation. Pi is the stationary visiting probability of a web page in a specifically designed random walk, or the PageRank authority measure, and we compute it by power iteration, right? So we use values for the right-hand side, recompute left-hand side, and iterate until sufficient convergence. So now we want to do it in a distributed manner. And this is not completely new. People have looked at this. So, no, okay. So something should be highlighted here, this here probably. So, and the work can be classified roughly into two camps. So one is where we go is a direction with coarse-grained block-oriented computations, or per-site computations, if you wish. So that does the following. It assumes there is high locality in these graph structures. And for example, because lots of links are within a site or within a domain, and there's very few that cross domains. And then we can, if that's the case, we can compute PageRank values within a block, and we also compute block rank values looking at a coarse-grained graph that consists of the blocks as nodes, and we combine the two in some fancy manner. So this works well if the assumption that we have this high locality and block structure, it holds true, and if we can make it explicit. For example, this is the adjacency matrix of the graph, if we really see this block diagonal structure. Now this is stolen from old Stanford papers, not so old, maybe 3-4 years old. And this is actually the Stanford domain and the Berkeley domain. So there were only two domains, and big surprise, locality holds here. I'm not convinced, we look at arbitrary web data, arbitrary block data, that we can identify these kinds of blocks. It's not clear if there is this block structure. It's not clear if, even if it is there, if we can find it, if we can make it explicit, because conceptually the matrix might then be commuted in terms of rows and columns, and we need to find the right permutations to see the block structure. Okay, so this is one direction. It also makes a strong assumption that these blocks are disjoint, which would be a burden in our setting. Now the other approach is a fine-grained message passing paradigm. So it really conceptually takes the power iteration steps to the finest granularity, namely per page. So when this is a page, and now in this power iteration, it propagates score mass, PageRank mass, to its neighbors. So, and this is done here, and if the neighbors are local, this is an efficient local computation. If the neighbor page to which it points sits somewhere else, it's a message that needs to be sent. Now, this is very elegant, but it's very inefficient. So maybe asymptotically it looks good on paper. I don't believe in this being practically viable because of the fine-grained message passing algorithm. So what we would like to do is have the block-oriented coarse-grained structure and the efficiency of that, and combine it with the generality of the message passing paradigm. And in addition, we would like to allow overlap between blocks. So we think of blocks, block equals peer, but now we have overlap, which was not addressed in this old work. So the overlap can be illustrated once again this way. So if this is a global graph, and now suppose we have 3 peers that have done their own personalized focus crawls, so they end up with these graph fragments that overlap. The same color should denote the same page, so some pages sit in multiple peers. Now, the approach that we've come up with, and that some preliminary version was in a workshop last year, and now a better version is in this year's VLDB. We've coined this JXP for juxtaposed approximate PageRank. It also happens to be the initials of my student, Josiane Xavier Pereira, but I'm the one who came up with a cool name. And it is based on Markov chain aggregation theory, so it builds on some existing theory, which has been used in other contexts too, for example, for incremental updates of PageRank measures. So Steve Tien and Langwell and Amy Langwell and Karl Meyer had some papers along these lines, also building on that theory for a very different purpose. So the idea is that from one peer's viewpoint, we collapse everything outside our own local graph fragment into one node. This is the state lumping technique. We call this the world node. And we compute a local PageRank based on this abstract graph, so our own graph fragment plus one node, the world node. And we increasingly refine knowledge about that structure, that abstracted structure with a superstate, by talking to other peers. So we run random peer meetings, and whenever we meet some other peer, we exchange various data structures. One of them is I compare my PageRank vector for the pages that I know, which might be a small, very tiny fraction of the whole web, and I combine this with the PageRank vector that the other peer knows. I also exchange the graph fragments or some information about this. In particular, if I have my local graph fragment, I'm interested in neighbors of my graph fragment. I know my out neighbors anyway because there must be links in my pages, but I don't know my in neighbors. So if that other peer has some nodes that point to nodes that I have, that's interesting information, and we want to exploit this. So that's being exchanged. We build an enhanced local graph, but still using this abstraction technique with a superstate, and recompute PageRank and come up with a better PageRank estimate. So it's important to emphasize we keep this lightweight, so every peer always has data structures and performs computations, both space-wise and time-wise, that are in the order of that peer's general storage and computational capabilities. So if I'm a peer that can handle 10 million web pages, I will not be forced to build an adjacency matrix with billions of pages. And I will not be forced to run computations over a bigger matrix. It's always like essentially my data plus some other peers. So it's in the extreme case, if we didn't optimize this in a better way, it would be a factor of 2 in all regards, space and time-wise. Now, it turns out this converges to global PageRank. So we had experiments first, came up with the proof later. So the proof is in the VLDB paper, and I will give some intuition about this. Now, it turns out the convergence speed can be improved by biasing the random peer meetings. And so we have a little strategy, a heuristic strategy that we called peer-to-peer dating. I have one slide later on this. So the key idea is we prefer peers that actually give us valuable information, namely peers that have pages that point to pages that we have. Now that leads again to an overlap estimation problem, but not my pages against your pages, but my pages against the pages that you point to. So again, it turns out the MIPS synopses are very handy here too, and give us a very efficient technique for estimating these. And we prefer these other peers as our meeting partners. Now, this is the most complicated slide. So I have 3 slides that kind of illustrate the computations. Don't get lost in the math. We will focus on the pictures, and maybe on one of them I will explain one equation. So this is now a situation where we have 3 peers, G, F, H. There might be more, but we don't see them here. From the viewpoint of this guy, G, this is just the world, one node, nothing else. Now, initially, we don't know anything about the world. All we know is that there are some nodes there. We assume we have an estimate of the total number of pages overall. We know how many we have, and we can estimate how many are here. So we know how much random jump mass would be transferred here. Remember, here you should, everybody should know everything about PageRank, right? So random jumps is a common thing. And that leaves some transition probabilities unused, and this is used here in a self-loop of the world state. So this is no longer a web graph, this is a Markov chain model, but built after this special situation where we have a graph fragment and abstract everything else into one superstate. Now we meet one other peer for the first time, for example, this guy. So this is what we have, and we're interested in the in-neighbors. So we realize there are two in-neighbors. From the other guy, we figure out the out-decrease. So we know essentially a transition probability from these blue guys to the node in peer G to which they point to. So if we know that, and if we also knew, this is actually now this part here. So we collapse them again because we don't want to blow up the computation. We want to work with the world node. So both of these edges, or there could be more, right? So they all collapse into one super edge from the world node to wherever they point to. And so we need to, for the computation, we now need a transition probability from a world node to the target Q. That's the random jump part, and that's the part how much mass is being transferred there. Now, if we knew the PageRank, the exact PageRank, or in Markov chain terminology, this is the stationary visiting probability of a state. If we knew this phi of p exactly, we could do an exact aggregation, disaggregation technique. So state lumping would lead to exact values, but that requires already solving the problem, so it doesn't work. So instead we use estimates. So pi star means whatever estimate we have for the PageRank of that page P, and that comes from the other peer. So we just take what the other peer offers to us. So that's only an estimate, right? And then essentially this tells you, so the transition probability is what's the probability of being in that state P, in that page P, given that we are outside of G, times probability that we follow a link, times divided by out degree, because every link is equally probable. Now we remember actually this information, so we remember information about in-neighbors because we can reuse this later on. Now if we meet the next guy, H, there's one node pointing to us, and now all that together is abstracted into the world node and multiple transitions, so all the three blue nodes. So, and that leads to transitions from the world node to two different targets. Again, using the transitions have probabilities, and they are computed according to this. So that is the theorem we have. In a fair sequence of meetings, the scores actually converge, and they converge to the true global page ranks if the network didn't change or the web didn't change. Of course, if the web changes all the time or the network changes all the time, there's nothing to prove. It would still work reasonably well, but there's no theorem. Now, what is a fair sequence? That means if in an infinite sequence, every peer is met infinitely often. So there's no negligence of some peers, which would give us a bias that can no longer be corrected. So as I said...
so this means that it converge after
yeah, convergence is infinite, always. Yeah, there's a limit, right? So good question. So we don't have theorems about convergence speed, like convergence rate. Ideally, this is desirable, but the math gets hairy here. So, and there's simpler settings of PageRank variations where world-class mathematicians haven't come up with rate analysis. So we're back to experiments, and I have some on the next slide. The proof is partly based on that existing theory. But it's not, it took us a long time because there are gaps. First we thought, well, there's such an elegant existing theory sitting around for 20 or more years, and it should apply here, but it does not, because our setting is pretty different, because we have this partial knowledge of the underlying Markov chain. And so we needed some additional things here. So the key observations that are part of the proof are that for the world node, the JXP score always overestimates the true PageRank. The PageRank of the superstate is the sum of the PageRanks of its nodes, right? That's always holds here. And the JXP scores are non-decreasing, and at some point, non-increasing, sorry, and there's an additional theorem that at some point they must decrease and finally converge to the right value. And for all the other nodes that sit in our graph G, it's the other way around. Here we underestimate the true PageRank, and the intuition is easy here because we lack the information that we have in neighbors. So these in neighbors give us additional authority, and we lack this and gradually learn it, right? And this is the intuition, right? The hard part is that we don't overshoot or fluctuate, that we actually converge. So let's come back to this dating strategy. I learned that in the US there's a new, yeah, go.
The convergence algorithms, as well as the quality measures. How resilient are these algorithms to some nodes not cooperating or lying about?
Okay. Yes. So the question is about what if some nodes cheat? That's in my outlook, right? So we don't have a solution for this. We're working on this, right? So, like if my meeting partner lies about the page ranks of in neighbors, right? So it is subject to game here, right? So. Oh no! I believe in good society, certainly. No, we have some. We have some initial thoughts on how to get this under control. Not surprisingly, it's highly related to the recent work that others have been doing on link spam, because it's a related problem. So, coming back to the dating or meeting strategy, so I heard in the US there's something called a power date. So you meet as a male, and I think you can reverse it. You meet 10 women in 5 minutes each, right? And then you make up your mind which of them you really want to meet. Or actually both make up their minds, I think. And it can be reversed. Sorry if this gets the wrong message here. So the women also decide which of these guys they want to meet for real, and so I heard this exists in the US in areas like this one here. So we mimic this. So we do these short power dates by only exchanging very compact synopses, namely the synopsis about overlap between my nodes and your outgoing link targets. And for that purpose, we need to pre-compute maps on like a peer's pages and the peer's outgoing link targets. And then we compare two peers. I compare my pages against the synopsis of your outgoing link targets. And this way, I build up some candidate lists this way. So I can do this very efficiently with many potential dating partners, and rank them, and then using some greedy heuristics at some point make up my mind which of them do I really want to meet. And only then I exchange graph data and PageRank vectors and really go through some less lightweight computation. So this is some experiments. We're performing experiments on small-scale data. Here we're using Amazon data. This is not really web data, I realize this, using recommended similar products as links. It appears this way in the web pages. We also did experiments with small-scale web crawls that we performed ourselves, and they pretty much coincide with the trends. So there's no big difference here. So you see the convergence is reasonably good, both this is the number of meetings in terms of rank distances, this is foot rule distance, and in terms of score distance as well. And you also see the green curve is the one that uses this biased power dating strategy. So we also did experiments on query result ranking in this setting. So guess what? The JXP scores or authority scores, PageRank-style authority scores, can improve the result ranking. And it can also be used for the query routing itself, because you want to route not only to peers with high quality contents, but also highly authoritative pages, right? So that can be added also into that part. and ongoing work is peer trust measures. So if we can compute some trust measure, we can factorize it into the computations by essentially biasing. When we recompute something, we essentially dampen down the values that some slightly mistrusted guy gives us, right? But of course, we need to find also a way of computing these trust measures. And the idea, just very quickly, for those of you who are familiar with these link spam detection techniques, so one recent technique is comparing distributions of scores, because you can fake one score, but it's difficult to consistently fake an entire distribution. For example, your PageRank score should also be should typically follow a power law distribution, or at least the ones for the pages that share a common target or a common source. And so you can run essentially statistical techniques, and that gives you indications of whether this other guy is likely to tell the truth or not. Right, at least or he must be very smart in lying. I'm not saying this is a perfect solution. So, unless there are any questions now, so summary. So I emphasized, I think peer-to-peer web search is an interesting research topic, regardless of whether there is a business killer application or not. I think it leads to lots of insights and findings that will sooner or later find their way into some setting. And one of the technical key areas is distributed statistics management. So it's key to query routing, to estimators for quality, overlap, and other measures. And also, essentially, the peer-to-peer PageRank computation is also distributed statistics, if you wish, with some specific flavor, right? And therefore, specific results like the convergence theorem. The challenge is in making this lightweight and efficient and scalable, and that has two sides. So capturing global statistics is one thing, and then disseminating this to the places where it's needed might be a different thing. Of course, we've used the same mechanism for both. Distributed hash tables is essentially the mechanism that we've employed in combination with different other careful considerations, like the combination with hash catches, for example. Now, in terms of big issues further down the road, robustness to churn and cheating is a big issue. Cheating is harder than churn. And it's not clear to me if it's well defined. It might be inherently ill-defined. Even in current work on spam detection, I see this phenomenon. It's treated like an arms race. So you try to detect some anomalous patterns, but then the other party also adapts and changes this. So maybe this needs a real paradigm shift towards some adversarial theories here. And that hasn't been in the literature at all so far, right? So right now it seems that, yes, you're trying to use heavy calibers, but if the enemy really has the incentive to also boost its machinery and its cannons, they might do it, right? And then it goes on and on, right? So overlay networks is a charming paradigm because it would kind of pre-compute frequent decisions as opposed to making decisions in fine-grained manners per query, or we can pre-compute, but of course these networks must be dynamically maintained. So as the network changes, as the web changes, as interest profiles change, this needs to be maintained. So you can call these, they come in under different names, semantic networks, social networks. In my view of the world, this is all about statistical characterizations again, because true semantics is not in the computer, and social things are among humans also by definition, right? So what we do in the computer is mimic only shallow aspects of this, and capturing the statistics about this is the key thing. And finally, experimental evaluation is some meta topic that I found to be difficult too. there's no established benchmarking methodology for these distributed things. Even the peer-to-peer systems community, the way they experiment is they run it. I mean, there's no notion of reproducible. They would give these rocket science papers where they say, we ran it on Planet Lab on 500 computers, and then half of them died by some accident, and we lost only 3% of the data. There's nothing reproducible, there's no general insight, there's just anecdotic evidence of something. It's difficult to interpret. So the benchmarking methodology is a big issue here because we're combining IR with distributed systems. So even in IR, benchmarking has a culture with track and INEX and other things, but it has a hard time to keep up with the pace of the world evolving towards more challenging settings. Now, a large-scale testbed is one piece of that. So we've been thinking of running this in Planet Lab. But the difficulty is that Planet Lab doesn't have users, real users. So we would have to deploy our load drivers, and then Planet Lab doesn't give us any real additional benefit. So we might as well run on one of our clusters. We have a big cluster on which we can run these experiments. So if we have load generators, then why use the real system? We're not into issues like, do the firewall, well, there's no firewalls on Planet Lab anyway. Do certain idiosyncrasies of networking protocols affect our approaches. So we're not into this kind of game anyway. So Planet Lab, I have mixed feelings about this. So and instead of using load drivers, ideally we would have real users and capture their behavior. And that brings me back to a remark I made earlier, and that's a good concluding remark. So of course there is such information available, like query logs and click streams. So but it's in the possession of a few players in the world, like 3 to 5 players maybe. So if some sanitized versions of this, of course, right, could be made available to the wider research community, this would be highly appreciated. Thanks for your attention.